Ever stepped onto a frozen puddle and suddenly found yourself sliding? Ice is famously slippery, but have you ever wondered why? It's not just because it's smooth and cold. Plenty of smooth things aren't nearly as slick. Ice's slipperiness is unique, and it all comes down to what's happening at the molecular level. This mystery affects everything from glacier movement to how animals and humans get around in winter. So, let's dive in and uncover the science behind ice's slippery secret. Most people think ice is slippery just because it's cold, but that's only part of the story. If cold alone made things slippery, a frozen rock would be just as slick as ice. But it's not. The real secret? Ice has a super thin, almost invisible, liquid-like layer on its surface, even when it's well below freezing. This layer acts as a lubricant, letting shoes, skates, or even penguin feet glide with little resistance. So, while cold creates ice, it's the unique behavior of water molecules at the surface that makes it so slippery. It's a fascinating chain reaction, and it all happens at the interface between solid ice and whatever touches it. Let's look closer at what's really going on at the surface. Here's the real star, a super thin, quasi-liquid layer on the surface of ice, even in freezing temperatures. Scientists call it the pre-melting layer, a film just a few molecules thick, thicker as the temperature nears melting. The outermost water molecules are less tightly held, so they behave more like liquid than solid. This layer is always present unless it's extremely cold, much colder than most places on Earth. It acts as a natural lubricant, drastically reducing friction and making sliding possible. Think of it as nature's built-in oil for ice, letting skates, boots, or even boxes glide smoothly. This is why ice is so much more slippery than other cold, smooth surfaces. It's a fundamental property that makes ice unique. Have you ever wondered why ice is slippery, even when it's well below freezing? It seems counterintuitive, doesn't it? After all, ice is solid, and solids aren't typically known for their slipperiness. So, what's the secret behind this seemingly paradoxical phenomenon? Why do these surface molecules form a liquid-like layer? What makes the very top layer of ice behave so differently from the ice beneath it? It's all about molecular behavior, the constant dance and interactions of water molecules at a microscopic level. These molecules are never truly still. They're always vibrating, rotating, and jostling against each other. The intensity of this movement depends on the temperature, but even in solid ice, there's a surprising amount of activity. In solid ice, water molecules are locked in a hexagonal crystal, a highly ordered and structured arrangement. Each molecule is tightly bound to its neighbors, forming a rigid network. This crystalline structure is what gives ice its strength and stability. But at the surface, they're missing neighbors and can move more freely. Unlike the molecules deep within the ice, surface molecules don't have other molecules above them. This lack of neighbors creates an imbalance of forces, allowing them to break free from the rigid crystal structure more easily. This gives them extra mobility, allowing them to slide and glide across the surface with relative ease. They're not completely free like in liquid water, but they're certainly not as constrained as the molecules within the ice. So they act more like a liquid than a solid, forming a thin, quasi-liquid layer on the surface of the ice. This layer is only a few molecules thick, but it's enough to significantly reduce friction. It's a natural result of surface energy, the tendency of molecules at the surface to minimize their interactions and achieve a lower energy state. Molecules at the edge want to minimize their energy, and one way to do that is to become more disordered and less tightly bound. So they become more disordered, breaking free from the rigid crystal structure and adopting a more fluid-like arrangement. This disorder is key to the slipperiness of ice. Imagine people at the edge of a crowd. They have more freedom to move around compared to those in the center. They can shuffle and move more than those packed in the middle, navigating the periphery with greater ease. They aren't bumping into people constantly and can change direction much easier. This increased mobility creates the slippery, quasi-liquid layer, allowing objects to slide across the surface with minimal resistance. Even at sub-zero temperatures, this layer is ready to reduce friction instantly, making ice skating possible and winter walks a bit treacherous. That's why ice is always a little bit slippery, no matter how cold it gets. It's a fascinating example of how molecular behavior can have a significant impact on our everyday experiences. There's another twist: pressure. When you press down on ice, like with a skate blade, you concentrate force on a tiny area. For ice, pressure actually lowers its melting point, so the ice under the blade can melt even below freezing. This creates a thin film of water right under the skate, acting as a lubricant for smooth gliding. As the skate moves, the pressure is released and the water refreezes. But pressure alone can't explain all of ice's slipperiness, especially at very low temperatures. At extreme cold, the pressure needed to melt ice is huge, more than a skate can provide. So pressure melting works together with the ever-present surface layer and another factor, friction. Let's see how friction adds to the story. Friction is the third key player. When you move across ice, friction generates a tiny bit of heat. Even a small amount of heat can melt a micro-thin layer of ice, especially if it's already close to melting. This frictional melting adds to the lubricating film, making sliding even easier. At very low temperatures, frictional heat might be the main way extra meltwater forms under your boots or skis. So, the slipperiness of ice comes from a team effort. The quasi-liquid surface layer, pressure melting, and frictional heating. Together, they create the perfect conditions for slipping and sliding. That's why ice is so reliably slick, whether you're skating or just trying to walk. We've explored the fascinating science behind ice's slipperiness, delving into the molecular dance that creates a thin layer of water on its surface. But how does this seemingly simple phenomenon play out in the real world, influencing the way we interact with icy environments? Let's take a look at some examples. Take ice skates. The very design hinges on this principle. The narrow blade, far from being a hindrance, is actually key to the magic. That narrow blade creates concentrated pressure on the ice beneath. This pressure, combined with the inevitable friction as the blade moves, adds heat to the equation. And remember that surface layer we talked about? It's always there, a crucial intermediary between the solid ice and the gliding skate. This combination of pressure, friction, and the ever-present water layer is what allows skaters to glide so effortlessly across the ice. It's a beautiful demonstration of physics in motion. It's what makes those incredible spins possible, the kind that seem to defy gravity. The skater is essentially hydroplaning on a microscopic film of water. But what about creatures that live on the ice, penguins? How do they manage? Well, their feet are specially adapted for icy conditions. They have rough, textured skin that provides a degree of friction, and sharp claws that can dig into the ice for extra grip. It's a natural anti-slip system, but penguins are also clever. They also use ice's slipperiness to their advantage, often choosing to slide on their bellies for quick and efficient travel across long distances. It's like a built-in toboggan. And what about us trying to navigate icy roads? Car tires. Winter tires are engineered with a specific goal in mind, to maximize grip on ice and snow. They use special rubber compounds that remain flexible in cold temperatures, and aggressive tread patterns designed to bite into the slippery surface. These tread patterns also incorporate channels and grooves that effectively channel away the thin water layer, allowing the tire to make direct contact with the ice beneath and maximizing contact. So whether it's a skater gracefully gliding across the rink, a penguin confidently waddling across the ice, or a car safely navigating an icy road, everyone's ultimately dealing with that same slippery surface film, that microscopic layer of water that dictates how we interact with ice. Understanding the science behind this slipperiness isn't just an academic exercise. It helps us design better equipment, from skates to tires, making winter activities safer and more enjoyable. And it allows us to appreciate the remarkable adaptations that animals have developed to thrive in icy environments. It's a great example of how basic science shapes the world around us, influencing everything from sports to technology and the natural world. So next time you see someone sliding, or hopefully sliding on ice, whether it's intentional or accidental, remember the fascinating science at play beneath their feet. It's all connected, all influenced by that incredibly thin, almost imperceptible watery layer. People have wondered about slippery ice for centuries, but real scientific investigation began in the 1800s. Michael Faraday noticed that pressing ice blocks together made them fuse, hinting at pressure-induced melting. Later, scientists like James Thomson described how pressure lowers ice's melting point. But pressure alone didn't explain everything, especially why ice is slippery even when you're just standing still. Only in the last few decades, with advanced tools, did scientists directly observe the quasi-liquid surface layer. Techniques like X-ray scattering and atomic force microscopy confirm that surface molecules are more mobile and disordered. It took many years and brilliant minds to piece together the full story of why ice is so slippery. So, after all this exploration into the fascinating world of ice, let's get down to brass tacks. What's the real reason ice is so slippery? What are the underlying factors that contribute to this common, yet complex phenomenon we experience every winter? It's not just one single thing, but rather a fascinating combination of three key elements working together in harmony. These elements create the perfect conditions for that characteristic slipperiness we associate with ice. First, we have a naturally slippery, quasi-liquid surface layer. This layer isn't quite solid ice, nor is it fully liquid water, but exists in a unique state somewhere in between. It's this in-between state that gives ice its initial slipperiness. Second, there's the phenomenon of pressure melting, which occurs under concentrated forces like those exerted by skate blades. The pressure causes the ice to melt, creating a thin layer of water that further reduces friction. And third, we have frictional heating, which is generated as you move across the ice. This friction creates heat, which in turn melts a small amount of ice, contributing to the lubricating layer of water. This incredibly thin film of water, created by a combination of these factors, acts as a lubricant, essentially a microscopic layer of liquid that sits between the ice and whatever is in contact with it. This lubrication is what allows feet, skates, car tires, or anything else to glide across the ice with surprisingly little resistance. It's like a microscopic slip and slide. The relative importance and contribution of each of these effects, the quasi-liquid layer, pressure melting, and frictional heating, changes depending on factors like the ambient temperature, the speed at which you're moving, and the amount of pressure being applied to the ice. But when all these factors come together, they create the unique and often treacherous slipperiness that we all associate with ice. It's a delicate balance of physics and chemistry in action. Understanding this science isn't just an academic exercise, it has real-world applications. It helps us design safer tires that can grip icy surfaces more effectively, reducing the risk of accidents. It also leads to the development of better sports gear like ice skates with enhanced blade designs, allowing athletes to perform at their best while maintaining control on the ice. And, perhaps most fascinatingly, it helps us understand how animals, like penguins and polar bears, have adapted to move efficiently and safely on icy terrain. So, the next time you encounter a seemingly innocuous patch of ice on the sidewalk, take a moment to remember the intricate molecular dance that's happening beneath your feet. Even a seemingly simple slip and fall on the ice is, in reality, a captivating showcase of amazing physics and chemistry principles at play. It's a reminder that science is all around us, even in the most unexpected places. Science is truly everywhere. It's woven into the fabric of our daily lives, shaping the world around us in countless ways. It's present even in a comical winter wipeout, reminding us that even our stumbles can be opportunities for learning and discovery. So keep exploring, keep questioning, and above all, stay curious about the world around you.